be talking about some models that we develop in my group, and they are stochastic models that we use in macroevolution. And the goal of these types of models are really inference models that we aim to statistically adjust to empirical data. And I'm going to be talking mostly about what we call comparative data. Those are empirical phylogenies of species, so species trees, and the phenotypes, the trait data that we can collect today on species that are alive at the present. And we want to use this type of data to test hypotheses about the evolution of life. So we have data we collect today, we reconstruct phylogenetic trees, we collect trait data, and then we want to have some stochastic models that allow us, by adjusting them to the data, to answer questions such as what are the modes of evolution, what is the tempo of evolution, the speed of evolution, how does it vary across the tree of life, what makes evolutionary rates vary, and are evolutionary rates at different levels of organization related to one another, and how. So the different levels of organization that I'm going to talk about are genes, phenotypes, and species. But first, I just want to say a small word about the type of statistical techniques we use to adjust the stochastic models to empirical data. And so those are either maximum likelihood inference. In this case, we really need to have ways to be able to compute the likelihoods associated to our models. Bayesian inference. Recently, we've started to use data augmentation. When we don't know how to compute likelihoods, we use approximate Bayesian computation. For some particular questions, we use penalized likelihood, and we also started this is still exploratory to use deep learning. So those are just like the statistical techniques we might use to adjust our models to the data. Now, in terms of the models, as I said, we're trying to understand modes and rates of evolution at 3 different levels of organization: at the genetic level, at the phenotypic level, so traits of organisms, for example, body size, and species level. And for these 3 types of questions, we either develop models that aim to model how DNA sequences evolve, so models of molecular evolution, how traits evolve on phylogenies, models of phenotypic evolution, and how diversification proceeds. So in this case, it's models of diversification. And I'm going to detail later a little bit more how these different models are constructed. By adjusting these different models to comparative data, we can estimate parameters of our models that most often are related to rates of evolution. So for example, we're going to be able to estimate rates of molecular evolution, rates of substitution, rates of phenotypic evolution, or rates of diversification. So for example, the speciation rates and extinction rate of species. So I'm first going to present the case of constant rate models, so the easy models that give an idea of the general principle of these modeling approaches. And then I will go in more details about how we go about modeling temporal rate variation and its underlying determinants, rate variation across lineages, and models with punctuated evolution. Okay, so the constant rate models, if I start with models of molecular evolution, what we aim to do here is to model the evolution of DNA sequences. So we have a sequence of a given fixed length, and we're trying to model the evolution of this sequence on a fixed ultrametric bifurcating species tree with branch lengths that are calibrated in unit of time. And here, for the purpose of my talk here, I'm going to assume that this phylogeny is known and fixed. And in this case, we have a sequence where each site evolves according to a constant rate matrix scaled by a constant substitution rate mu. And the assumption is that each nucleotide site evolves independently, and so we can compute the likelihood of alignment as a product of the likelihood of each individual site. And we can compute these likelihoods using a well-known algorithm, the Felsenstein algorithm. And so this is to illustrate the idea of these models. If we're able to compute these likelihoods, which we are able to do, then we can estimate the substitution rate mu by maximum likelihood or Bayesian inference by finding the parameter that maximize the likelihood of our alignment, the probability of our alignment. Same principle for models of phenotypic evolution. Here again, we assume that the phylogenetic tree of species is fixed and known, and we're going to evolve a trait value. We can think, for example, about body size on the fixed phylogeny. One of the easiest and most used way to do that is to use a diffusion process. So here, for example, the simple Brownian motion process, where in a given unit of time, we're going to have a normal deviation from the ancestral value. For these types of models, we are able to compute likelihoods of trait value of the tip of a phylogeny under these processes. They are multivariate normal distribution with a given variance covariance matrix that we can that, for example, in the case of the simple Brownian process, is given by the evolutionary rate parameter, the rate of a Brownian process, times the evolutionary history shared between the species. So here, for example, if we look at the expected covariance in trait values between two species, it will be proportional to the evolutionary rate and to the time since the origin of the clade to the divergence between the two species. So same general principle, we're able to compute the likelihood, and this gives us the possibility to maximize this likelihood and to obtain estimates of our parameters. So here, estimates of the rate of phenotypic evolution. For models of diversification, we use stochastic birth depth models, so like same type of models that are used in population dynamics, where we have a given birth rate, which here is interpreted as the speciation rate, and a birth rate, which is death rate, which is interpreted as the extinction rate. What we're able to do is to compute the likelihood of a reconstructed tree, so the tree of the species that are alive today under this process of constant rate speciation extinction. And so if we use, again, maximum likelihood of other types of statistical techniques, we can estimate the parameters lambda and mu, which we are interested in, so the speciation rate and extinction rate of species. Those are the easiest constant rate models that we use to model molecular evolution, phenotypic evolution, and diversification. And then there are extensions on these models that allow to test how rates of evolution might vary as clade evolution proceeds, and what might make these rates vary. In particular, so I'm going to start with models of diversification and phenotypic evolution. The reason why such models have been developed is that there has been some verbal arguments that rates of evolution might, for example, decrease through time. And the idea here comes from the idea of adaptive radiations, that is the rapid phenotypic and species diversification of clades, which is supposed to come from competition. And so the idea here is that as niches are unoccupied, we're going to have fast diversification of species and traits, and as niches are progressively filled as evolution proceeds, we're going to have a decline in rates of evolution through time. So in order to be able to test whether adaptive radiations occur in nature and how frequent they are, evolutionary biologists have used these types of ideas and tested, and they wanted to test whether we see in empirical phylogenies a signal of declining evolutionary rates through time. So we can compute the likelihoods of such processes as well. So here it's just a simple extension of the traditional constant rate birth depth model, where we have now speciation rate and extinction rate that can vary as a continuous function of time. Here we use parametric functions. So for example, we can try for an exponential decline in time, or linear decline in time, or like any type of function, parametric functional dependency with time. And we can also have a process where at present we sample a given number of species. So that allows us to then apply the models to phylogenies that are not completely sampled. So at present we sample randomly some of the tips in the phylogeny, and we're still able to compute the probability and to the likelihood of the time points in the divergence times, the times of speciation in the reconstructed phylogeny, so in the field phylogeny of present-day species. Just to give you an idea of how the different components of this likelihood expression are computed. Usually, for example, we need probabilities such as the probability that a lineage alive at a given time doesn't leave any descendant in the sample at present. And so to obtain this type of probabilities, what we do is usually to see how to write down this probability at times t plus delta t as a function of a probability at times t. So for example, here, if we're talking about the probability that a lineage is not sampled at present, given that it was alive at time t, we write what can happen during the time delta t. Either the lineage goes extinct, or it doesn't go extinct. There's a speciation event, and the two descending lineages go extinct. Or there is no extinction event, there is no speciation event, and the lineage goes extinct. And then the other things that can happen are in O delta t, and so we can obtain the differential equation that describes the variation in this probability, and we can solve this equation and find an analytical solution for example, this probability of extinction. But we can also find using the same idea these probabilities to observe each branch in the phylogeny, and at the end we can have an analytical expression for this likelihood. So we are able to obtain such likelihoods even when with rates that can vary through time. And so if now we apply these models to empirical phylogenies, what has been found is indeed a pretty ubiquitous support for these types of models on empirical phylogenies. So we tend to see a signal in empirical phylogenies of time varying rates, and in particular in rates of speciation that decline through time. So something that would go in the direction of support for this idea that there can be adaptive radiation in nature. But what we have thought about is because we see this signal a lot, and it seems maybe a little bit magical that all these clades have a support for declining rates, which means that they would all follow this process of adaptive radiation and filling of niche space. And we thought about all the different reasons or processes that could lead to this signal of declining rates in molecular phylogenies. And that's where then we want to develop models where we can test for the effect of covariates. So for example, an alternative hypothesis that we thought about is that this could be an effect of changing climate in Earth's history. So during the Cenozoic, there's been a general cool down in temperature through time. And there's several theories in ecology, for example, the metabolic theory of ecology, that suggests that there should be a positive relationship between external temperature and evolutionary rates, some rates of molecular evolution that would then go up the chain of different types of evolution and potentially spur speciation events. So if we want to be able to test this type of hypothesis with our models, we need to develop models where our rates of speciation and extinction can depend not only on time, but also on a set of measured environmental variables. So for example, if we have data of how temperature changed through Earth history, which we have kind of data that gives that, then we can test whether there is an effect of this past environmental variation on rates of diversification. So here again, an empirical application of this type of models that was carried that we carried across tetrapods, and where we basically compare these models with a climatic dependency of diversification rates to models where rates are either constant through time or vary as an effect of diversity-dependent processes or different types of other potential processes, and we can use different potential functional dependencies of rates on temperature that can be potentially can come, for example, from predictions from the metabolic theory of diversity or other types of theories. So when we fit these models to empirical data, this is an example of the results we find. So first, when we compare models with time varying rates to constant rate model, we do find a pretty strong support for models where rates are not constant through time, and in particular support for models where rates of diversification tend to decrease through time. So this general pattern that I told you before was quite ubiquitous in phylogenies. We find again here across a large range of tetrapods. Now, when we look at the support for models where we include temperature dependency in the rates of diversification, the support is mixed, so it's not like an overwhelming support, but there is a significant fraction of a phylogeny where models where rates vary as a function of temperature are more supported than models where we have dependency of the rate. So just, for example, a declining rate through time. And when we do find a support for temperature-dependent model, we tend to find support for positive dependency, meaning that we find that speciation rates are higher during periods of warm climates, so faster speciation under warm climatic periods. And if we look on individual clades, the type of temporal trend that this gives, example here that would tend towards a trend of declining speciation rate through time. And this is because we have this cooling down of the temperature during the Cenozoic. If we have a positive effect of temperature on speciation rate, then we have a decline in speciation rate. So this is to say that, not to say that, okay, this is the explanation of why we see so many declines in speciation rate through time, but a potentially alternative explanation, and one that finds as much support in empirical data than models of adaptive radiation, for example. This same type of models where we want to model how evolutionary rates might have varied through time, we already have such models to look at phenotypic evolution. And in this case, also a simple variation from the simple Brownian process where we can put functional dependency, functional type dependency in the evolutionary rate, which measures the speed at which phenotypes evolve. And again, here we still have a likelihood which is written as a multivariate normal distribution, and in this case the variance covariance matrix can also be computed analytically, and it's easily found by solving some simple integrals through time. So that means that we can adjust these models to data and compare their support on empirical data. In the case of phenotypic evolution, people haven't found that much support for models with declining rates of phenotypic evolution. So here in yellow, we see the support for a constant rate model, the Brownian motion process. SSP is a model, it's the Horsten-Uhlenbeck process that models evolution towards an adaptive peak. And the early burst model, which will be the model with a time decline in speciation rate, is not supported in many empirical data. Same thing here. What we wanted to develop models where we can test for the effect of change in past environmental variables through time on rates of phenotypic evolution. And again, here this can be done by integrating some covariates in our parameters and integrating that in the computation of the likelihood. And that allows us to compare different models of trait evolution and to test the potential effect of past climatic change on rates. So here we applied that to the question of body size evolution in mammals and birds with big data sets that are publicly available of phylogenies and trait data at the tip of, at the tip of the phylogeny, and used a temperature curve across the Cenozoic, and again fitted different types of dependencies of the rate on past temperature. Here are the results. Here, what we find is this pretty overwhelming support across different bird and mammal family for models where there is dependency of evolutionary rate, the rate of trait evolution, on temperature on this rate of evolution. And when we look at the sign of the dependency, so can be looked at by the estimation of a parameter that controls the dependency of a rate on past climate, there is a general tendency for this rate to be negative, and again pretty consistent across groups. That suggests that rates of phenotypic evolution are faster during cold rather than during warm geological periods. And in this case, this would result in an increase in evolutionary rates over the Cenozoic, not a decline in evolutionary rates over the Cenozoic. So what we find is that temperature seems to influence rates of diversification and body size at the macroevolutionary scale. For diversification, we found a positive effect of temperature on rates of evolution, but for body size evolution, a negative effect. So for faster evolution under a cold rather than warm climates, and this is this later result is contradictory to expectation under the metabolic hypothesis, and it suggests indeed that it's more like increased selection that can happen, increased pressure under cold climate where there's faster climatic variation and over processes that leads to faster evolution. So just because here I always like put in perspective these different models of that all model rates of evolution, but at different levels of organization, it is notable that although like these models have been pretty important and widespread in the literature on phenotypic and species diversification, those types of models where there's a time dependency in rates haven't really been explored in models of molecular evolution. And I don't know if it's because there hasn't been like the same type of theories of adaptive radiation that have driven the wish to develop such models, but they are not really present. So we don't really have a test for variation in rates of molecular evolution, at least in time, in the current literature. So something else that can be really important also in all the models that I presented so far, there was the assumption that rates were homogeneous across lineages. So at a given time point, all lineages in the phylogeny in the clade have the same rate. However, we know that there's a lot of different reasons, like different life history traits or different habitats that are going to potentially influence rates of evolution. And so it's pretty important to model this type of variation. The way that this has been done, and this has been done a lot in models of molecular evolution, this is basically to relax the molecular clock, right? So in models of molecular evolution, when we have constant rate, it's a constant clock model of molecular evolution, and there has been a lot of effort to relax this hypothesis, and in different ways. So either we consider fixed or random local clocks, where in localized portions of a phylogeny we are going to have a constant rate, but this rate can shift from one background rate to a faster rate, for example. Or the other way to model rate variation has been to use relaxed clocks that are either uncorrelated. So here we can just draw different rate parameter in a given distribution, but so the distribution is fixed, but the rates are not inherited. So there's no, the draws are done independently. Or we can have another idea of evolution where rates are rather phylogenetic constrained, maybe because they are linked to life history traits that are evolutionarily conserved from ancestral species to descendant species. And in this case, we need to put together what we call correlated relaxed clock models, where there's going to be an heritability of a trait from parents to descendants. So this is very widespread in models of molecular evolution, and in models of diversification and phenotypic evolution, it's been pretty recent to develop these types of models. At the moment, or like until 1 or 2 years ago, the only models that were available to model variation in rates of diversification were the equivalent of local clock models, where we're going to assume that rates are shared between closely related species, and there's just times in history where there's a shift, a variation in the rates of speciation or extinction that is then shared between all descendant species. What we've done recently is to develop models that are closer to the correlated clock models from molecular evolution that allows to model much more subtle variation in speciation rates. So here the process is the following. We have a birth-death process, and at each speciation event, the descendants' lineages are going to have a new rate, which is drawn from the distribution centered or parameterized on the ancestral rate, but with a given trend, for example, a trend of declining rate through time, and a stochastic component. So like the wider the distribution and the less heritability we have, the tighter the distribution, the more heritability of rates we have. So in the end, this is a model that still has quite few parameters, only the initial speciation rate, a deterministic trend, the sigma that controls the heritability of the rate, and a parameter that controls the amount of extinction. And we can use MCMC to estimate these hyperparameters, but also to estimate all the parameters of the models, which then are all the speciation rates for each branch in the phylogeny. And so what gives us is the possibility, if we have a reconstructed phylogeny, to estimate speciation rates per branch specific rates of speciation and extinction, which is pretty useful in the community. So here what we see are results of simulation that try to see whether we are actually able to infer the parameters of hyperparameters of the model. So here we have the simulated sigma versus the inferred sigma, and we see that we are more, and the inferred alpha versus simulated alpha, and we see that we're more or less able to recover the parameters that we simulate from our process. So this is a good news. And when it comes to the branch specific rate, so here we have a simulation under the process and the inference, the inferred rates. What we see, and we see it better here, where we have a result of a bunch of different simulations, is that we tend to to lose a little bit of a variation, so the signal is smoothed, but we are still able to detect the trend. So we're able to detect like clades where there's been an acceleration in diversification or a slowdown in diversification. We're able to see these big trends. And then we can apply this to empirical phylogeny. So here we have two contrasting examples when we fit this model to two different bird clades. One where we see that the rates are pretty homogeneous. So an hypothesis of homogeneous rates in this particular group would not have been so bad. But others where there is a very big variation, like orders of magnitude variation in the rate of speciation. So where it's really important to account for such variation. And when we look for all bird families across the whole bird radiation, we find again like these examples of clades where rates are pretty constrained and examples where rates are very variable. And what we see here, we have a distribution of speciation rates in black for the whole bird clade and then for individual clade. And we see that for some of these clades, there's as much variation within the clade that across the whole bird phylogeny, meaning that there's really like some rate heterogeneity that can happen at a pretty narrow taxonomic scale. It's not that only big shift in diversification happen during the evolution of clades, but also at small scales, there can be a lot of variation. So yeah, there's for several reasons. I'm not going to go in detail here. It's quite useful for ecologists and evolutionary biologists to have these per branch rates of speciation, and our method is quite good at doing that, but it was pretty slow. So we put together, instead of the initial MCMC, which was based on analytical solution of the likelihood, in fact, when we used data augmentation, we can go much faster. And this is because we can computing the likelihood of a complete tree where we have the extinct branches is really easy and really fast. But when we want to compute the likelihood where we are missing, where we have hidden speciation events that are hidden because we don't have all the extent lineages, we need to solve some different systems of ODUs and integrals and so on that are quite long to compute. So in the end, using techniques such as data augmentation allows us to go much faster, and it also gives other types of inference. So for example, if we do that data augmentation, meaning that we augment the tree with all the extinct branches, then we can also look at other things, such as, for example, how the mean rate across all branches, extant and extinct, varies through time, or how the number of lineages, the number of species varied through time, and so on. So it's quite powerful to use this type of approaches, and we are increasingly using them. In terms of models of phenotypic evolution, the trend has been a little bit the same. So the models that exist at the moment are models where are local clock models, where people try to identify places in the phylogeny where there's been a shift in the rate of phenotypic evolution. For example, using reversible germ Markov-Chain Monte Carlo to estimate the number of shifts that happen in a given phylogeny and where. But same thing, there is a need for models that are more similar to the correlated clock models, and so we started to develop those types of models for phenotypic evolution. So, for example, what Julien Clavel here, who was postdoc in my group, is developing are models where we have the same as the independent clock model, so where we have branch-specific rates that are identically drawn independently and intensely distributed distribution. So here, for example, the log normal distribution. So here we have a evolution of a trait value, which is still a Brownian process, but the rate of evolution of this process is going to be drawn in a log normal distribution, and is able to find inference approaches for Bayesian inference approaches for this model. And then he also develops these models that are called stochastic volatility processes, where the rates are inherited at speciation event, and the rates themselves follow a geometric Brownian process. So here, same thing, we have the trait values that follows the Brownian motion process on the phylogeny, but the evolution of a rate is itself a geometric Brownian process. Oh, where are I missing all my empirical applications here? Oh, that's okay. Missing some slides, sorry, I don't know what happened. But yeah, what well, maybe I will have some empirical applications about that later in what happens here. Yeah, the last thing that people have or that we want to model in these processes of evolution, and in particular at the phenotypic of molecular levels, is the idea of punctuated evolution. So here, all the processes that I described are processes that happen anagenetically. So here, for example, we have the example for phenotypic models. There's a gradual variation, gradual evolution of trait values along branches in a phylogeny. And this is really the idea of a gradual evolution, but there's this alternative idea of punctuated evolution, where there can be periods of stasis with few changes, but then bursts of evolution, at a very rapid burst of evolution that at the macro evolutionary scale really appear as a punctual. And so in all the processes that I showed, this type of evolutionary process are not modeled. Yeah, there's been some efforts to include these jumps in trait values in the diffusion processes. So for example, using Levy processes, and this has already been developed to model the evolution of phenotypic data on phylogenetic trees. And when we look at the support for such models in empirical data, here we have the model support for either models with incremental change. So for example, it would be the stochastic, the simple Brownian process. Incremental stationarity would be an Horsten-Uhlenbeck process, where there is a constant rate, where there's a homogeneous rate across lineages, but with a tendency towards evolution towards an adaptive optimum. Explosive change would be the early burst model that I presented before, where there's a decline in rate through time. And the pulse change is a model that models the Levy process with jumps. And what we see here is that there's a lot of clades with a pretty strong support for these models, where there is punctuated evolution. However, we can think that these types of punctuated evolution, they don't again occur in a background rate of phenotypic evolution that is homogeneous across lineages, but on the contrary, on a background that is variable across lineages. So in the type of models that Julien developed, he added this jump process. So we have the stochastic volatility processes with rates that can vary across branches in the phylogeny, but we add periods of jumps in trait values, and with different possibilities to model the jumps. And when we do that, this is pretty preliminary result, but what is highlighted in red are the models that receive the most statistical support. And what we find when we consider both the variation in rate and jumps is that the models with pulsed evolution are not supported anymore. So here, the models with both trait variation and pulsed evolution are the ones that are at the bottom of the table, and they are usually not supported. The models that are the most supported are models where there is autocorrelation in rates, but no jumps. So just to illustrate how, like, considering different sets of models can really change our idea. Like from this result, we have the idea that, okay, maybe pulsed evolution is super important to account for, but in fact, if we account for rate heterogeneity, it might not be so prevalent in nature. At the molecular level, it's also like the same thing, where it's really an idea of gradual evolution that has been modeled. So sequences experience substitution along the branches of the phylogenies. And what we did is to develop a model where, on the contrary, at speciation event, we can have a burst of molecular evolution with several nucleotides that experience substitution at the same time. So here we combine these two processes, a gradual clock-like model of evolution along the branches and these events that we call spikes that happen with a given probability at speciation. And when a spike occurs, each site experiences a substitution with a given probability k. This model, like this process, we can also put together an inference machinery, a Bayesian machinery to adjust it to data. And here that's what we did on genes that code for venom evolution in snakes. And maybe you don't see too well, but the dots are places where it's been inferred that there's been a spike in evolution in these genes. And when we apply these models to genes that are thought to be more neutral or not be related to particular functions, we don't find any such spikes. So it seems that this really can say something about some genes that have been like particularly adaptive and maybe related to speciation events. So yeah, with this, I think I'm going to conclude, just to say that all these tools, they can be applied to empirical data, and we put a pretty big effort in making them available to the community of evolutionary biologists. And so people use these tools. It's either like in a package that is devoted more to the modeling of diversification, and this other package, which is really led by Julien, which is more about phenotypic evolution, and also like things that I didn't show, like multivariate phenotypic evolution. And they are pretty powerful to when we have we still need to develop a bunch of tools, but once we have these tools and we have the data, it's pretty powerful to be able to really test these different hypotheses about how evolution proceeds, and also to estimate how rates of evolution, to estimate them and to see how they vary across different species with different habitat and trait value and so on. And then this really helps us to understand how biodiversity evolves. And what is striking to see, I find at the moment, is kind of a convergence between the ways that models have been built. So like these three fields didn't really appear maybe in this talk, but they have been developed a little bit independently. And so there are specific models that have been developed for which three different ways to look at evolution. And at the moment, there's really a convergence, and we're trying to go towards like this convergence of models, for example, using a geometric Brownian process to model both phenotypic evolution and rates of molecular evolution, and why not rates of speciation. And if we're able to do that, then that can really help us to have a common framework to estimate rates, and potentially also build joint models of phenotypic evolution and diversification, or molecular evolution and diversification, and so on. And we can really try to better understand also how evolution at these different evolution levels of organization is related, and try to understand, like, yeah, when we have a correlation between these different types of evolutionary processes, and why. So yeah, with that, I'm done. I thank you for your attention, and can take some questions. Hello.
Thanks a lot. So
yeah.
that's a very nice talk, and I want to thank you very much for your very nice presentation. May I? So there are definitely thousands of questions which are possible to consider in such a presentation, and I think it would be great if you agree to come back maybe in the afternoon for this round table.
Yeah, so I would love to, but I learned yesterday that I'm a contact case of COVID, so I need to go get tested.
Okay, so
yeah.
But anyway, I would be very happy if we can.
During the round table, but
I would be very happy if there is a way to keep in touch.
Sure.
Okay, so thank you very much, and I don't know. In fact, that's I gave you a very complicated position because you are both the chairman and the orator. So I don't know what to say. Maybe the second talk is almost 15 minutes from here. I guess in the spirit of the whole conference, it would be more reasonable to make just a break and come back on time.
I don't know. There's no question. You didn't.
Sorry.
Sorry. There's some question that we can break now if you want.
Sorry. I am awful. Sorry.
No question.
Okay. I can ask a question, but I forget what you explained. We have to write the question in some chat.
There is a chat box. If you are not in the full screen version, then you just have the list of participants, and you can just send a chat, send a message for the whole people, and maybe I think you can make also private message.
Okay, but if there's a question, maybe
sorry, that Tran. Okay, sorry.
But sorry, it's my fault. But if there's no question, I can maybe ask one to Hélène.
Yeah, sure. Yeah.
So thank you very much for your talk. I like it very much. And maybe with Sylvie and Sylvain, we try to do something a bit of that sort, where we try to explain the change in the rates of diversification and extinction by interactions due to the phenotypic traits.
Okay.
And do you think that it can be relevant, and can you think that this could be tested on your data, whether the interactions that your model generates, for instance, could be due to interactions between your different species?
So are you talking about how at the beginning I thought you were talking about how some specific traits might affect diversification, but at the end interactions, so you mean interspecific interactions or traits?
No, well, interspecific interactions, but through traits.
Interspecific interactions through traits. So, okay, we were not able, or we haven't yet developed models that we can fit to data where the interaction between species affects directly rates of diversification. We haven't developed these models. Maybe that's what you have done with Sylvie and Sylvain. What we have been able to do is to develop models where species interactions affect trait evolution. So not diversification, but trait evolution. We developed models in particular where we can model character displacement, so competition between species with similar traits are going to generate a character displacement where traits are going to be repulsed from the trait values of other interacting lineages. But in terms of modifying the rates of diversification, we haven't done that yet. We have a simulation model, but we're not able to develop likelihood inference approaches and things like that. So maybe
okay.
Discuss, yeah.
So maybe I missed it in your talk, but it relates to one of the part of the talk, or it's something that is new and
I didn't talk about it. I just because
yes.
I didn't talk about it. But I didn't talk about it here.
Okay, but I would be interested to to talk further about it. If
Sure. Yeah. It's really something that still needs to be done in the field to have these models where we have species interaction affecting diversification rates.
Okay, thank you very much.
Yeah. There are other questions or not really? No. So Paul, you want to then come back at 10? That's what you said?
I guess it is more reasonable because I don't know if people want to attend the talk by Alejandra, especially. I don't know exactly. So I want due to the very strange way of communication, I think it's better to have a very strict schedule.
Yeah, sure. I don't know if you want to stay online by this time, if you want to see like some models of phenotypic evolution, like interspecific interaction.
Oh, you are welcome.
Yeah, okay, I can show that. I gave a talk at 7 a.m. in Australia. It's the day today. So, and this was about, I focused more on the role of species interactions. So, and of like if like it seems like some people are interested, and since we have 10 minutes to kill, okay, so what can I, are you more interested in a model that's more like a simulation models that look at the effect of competition on diversification, or something that is an inference approach?
No, simulations are fine if you have some nice simulations. Yes.
Well, I don't know.
I agree.
Everything is fine.
Everything is fine. Okay, but so here, like this is the example of model that we developed to, in particular, to test, this hypothesis that this verbal expectation that rates of diversification and phenotypic evolution should decline through time as a result of competition. So we developed this simulation model where we try to model the effect of the model of competition on the evolutionary process. And so this model, it's a model of protected speciation, where there's it's still a lineage-based model. It's not individual-based, but it's a lineage-based model where we can have initiation of speciation. We have incipient lineages. So those are two subpopulations that can either at some point become really like distinct species, or one of them can go extinct and then you don't have a new species, or you can have secondary contact and so on, and then this is not making a new species. And once we do that, then we have a possibility to model what happens, like the role of competition in driving divergence, because that's like what the goal here, to see what can be the role of competition in driving phenotypic divergence and in the end diversification. So here, for example, the way that we model that is something where the trait value of a given lineage is going to experience character displacement. So it's displaced from the trait values of other species that it interacts with, right? So if you have if you are close phenotypically to other species, there's going to be a pull towards characters that are distinct, and the stronger this alpha parameter and the stronger this repulsion is going to be. So alpha kind of measure the strength of competition in displacing traits, displacing characters. So that's the first role, is the role of competition on character displacement, and that allows to model how competition might drive or not divergence between subpopulations. So here, what's going to happen is that in these incipient lineages, once character displacement has been large enough, then there is a rate of completion of speciation that is higher. So character displacement driven by competition is going to foster a speciation completion. And finally, the other effect of competition is potentially to drive competitive exclusion. So we have an effect of trait values on the probability for given lineages to go extinct. And here it's the same. The more we have lineages that are phenotypically similar, and the higher the extinction rate. And this depends also on the strength of competition alpha. So the results we found, like same at the macroevolutionary scales, in terms of testing these expectations of whether we should expect a decline in rates of diversification and trait evolution driven by competition. We do find this effect on diversification rates. So when you increase the strength of competition alpha, you have a stronger decline in diversification rate. But in trait evolution, we tried a lot of things, bonding trait space and doing a bunch of different stuff, and we were not able to generate this decline in rates of phenotypic evolution that verbally people seem to expect from adaptive radiations. So just like an example of how this is included, for example, here in simulation models, but for example, we don't have yet an inference procedure for this model. We're not able to fit it to data, and we started to put together an ABC approach for doing it, but it's not super straightforward. I don't know if this is like the type of models that we were thinking about or not at all.
Yes, okay. A bit, not exactly like this, but
well, I mean, there's different ways to do it, and this here is an other model where this time it's individual based. So really, where we look at the effect of. So here, I think maybe it would be closer to the type of models you develop with Sylvie and Sylvain. Where the phenotype of a given individual is going to influence its fitness. And the fitness is modeled on reproductive rates, and the difficulty, I don't know in your models how you generate diversity, how you make speciation happen. Here, even in these models that are individual based, the problem is then we don't have a rate of speciation anymore, right? In the other models that are lineage based, you just have a rate of speciation, and then you generate diversity in this way. When you have individual based models, and then there's mutations happening on these individuals, the way that we did here in this model is with this model that we developed with Amaury, also the speciation by genetic differentiation, where we're going to cluster individuals based on neutral mutations that happened on these on genealogies. But I think it's really the weak part, or the difficult part, is how to cluster individuals together into species once you work with individual based models.
In fact, the species can be defined. Sorry. I don't know if we have much time to discuss, but you can try to define that individuals belong to species, so you can compute diversification rates. And in fact, in some of your slides, you change the different rates at each speciation event.
Yeah.
And in fact, it was a bit our idea to say that, well, it's not our idea, it's a general idea, but to say that the change, instead of just drawing in some given distribution, the distribution depends on the distribution of other species, and it also influences, it has a retroaction on the different species.
Okay. Cool.
And it's a bit like yours, but the difference is that the rates, they vary according to the displacement of the species, and even in one species which survives, if it has more and more competitors, competitor species around it, it can also decrease its rate because it becomes more challenged and
cool. Yeah, no, that's yeah,
something like this.
Yeah, okay. And so, in terms of inference, you're able to
yes.
Yeah.
In fact, we can simulate also the model very easily.
Yes.
So we did a bit like what you presented at some point. We can do ABC or things like this, but it's not very precise inference.
Yeah, yeah. It's you have identifiability issues or things like that. Yeah.
Yes, and the model are very precise. So often you have a very the a posteriori distributions are not very good.
Okay.
If the model is too generic, for instance.
Yeah. Okay. Cool. Yeah, that sounds great. I'd be happy to see that.
Yes, should try to discuss more one day.
Yeah. Nice. I think we're going to. It's time now to move on. It's good. We had our little break to chat. Let's see. So, do you want to? Let's see. Okay. I'm almost there. Okay. So next is Alexandra Cabana.